Also going to talk about the macrospecies model, so it's macroscopic behavior in the two-species exclusion process. Please.
Hi, so thanks for having me. We talk about the two-species exclusion process. I've been working on with my supervisor, Maria and Rob. And we're going to look at it using matched asymptotics. So first of all, some motivation. Why look at a stochastic process? By the simple exclusion process. So stochastic processes are often found in biology. So for example, the movement of cells. So here, an example is chemotaxis. So we have a bacteria cell moving around, and with no stimulus, it kind of has this kind of run and tumble behavior. It's kind of random motion. But maybe if there's an external stimuli, some chemical, it will still move with some random behavior, but it will now be biased towards some given direction. But we also see this in collective dynamics. So, for example, a swarm here, a shoal of fish, where each individual fish will have some microscopic dynamics describing its motion. It might try to align itself with the motion of the fish around it. But this, if you describe this sort of microscopic behavior, this then leads to some larger macroscopic behavior of the whole shoal moving together. And also important within collective dynamics or movement of multiple species is volume exclusion. So here, there's an example of an ion channel where the barrier between a cell and the environment, there's particles sort of being drawn through, but there's a lot of it gets kind of clogged up when there's a lot of particles in the way, and so it's also important to quantify this kind of this volume exclusion and not allowing particles to overlap. An example where this goes wrong is if in chemotaxis and you have a large number of cells, if they're, say, secreting some chemical that attracts the cells to the same place, if you don't account for volume exclusion in your microscopic model, it then leads to blow up in your macroscopic model, where you then might have this sort of infinite density of particles, which you really don't want your model to predict, because that doesn't really happen in real world. So you try and include, with our exclusion process, we try and include some volume exclusion now in a microscopic behavior. So let's think about how we might construct a very simple model to start with. So we take a particle and we let it perform some random walk on a lattice. Here we set the lattice spacing to h. This is going to be on a microscopic scale, so h is going to be very small. And the particle is going to hop to an adjacent site with some rate lambda that we're going to fix later on. At the moment, it's just going to be constant, but later we might introduce some rule where it depends on the site that it's actually. So this is just going to sort of hop around on a lattice. And our lattice is embedded in a torus. So it's going to be periodic in each direction. So the particle gets to the edge. This sort of edge is same as the other edge on the other side. So if it hops again to the right, it's like hop around the other side. And so how would we describe this process using a PDE? Well, we have, first of all, we look at the probability density. And so here the factor of h accounts for, as we let h get smaller and smaller, the probability that you find a particle at the site, or the h to the d. So for this quantity to make sense, as we take h to 0, we look at the probability density. And so the Maxwell equation for this is like this, where this is the flow into the site x, and this is the flow out of site x. And this looks very much like a discrete Laplacian. So if we scale lambda as 1/h², this forms sort of a discrete Laplacian here. So if we took h to 0, this would converge to just the Hughes equation to gain sort of diffusive behavior of a particle. We could have a more complicated jump rate as well. So we could let lambda say depend on the position of the particle. So here lambda is the rate that when the particle is at x, be the rate that it jumps to an adjacent site, x plus kg, where is a unit vector. And here we choose the potential. So the idea is that potential is more likely to jump to a site with a lower potential. So over time, this sort of minimizes potential. And so if we assume V is smooth, we can Taylor expand, and then again take the limit. Where now we still have the diffusive term, but now we also gain this sort of drift term, gradient of V. Okay, so that might be one particle on its own. But how do we introduce an exclusion rule when we have two particles moving around? So we denote the state of our system by this variable eta, where it's 1 if there's a red particle, eta r is 1 if there's a red particle at that site, and 0 otherwise. The idea being this is going to work better later on when we have more particles. And so each particle moves with its own jump rate. So lambda r and lambda b for red and blue. And now so these hop around. But now when they're next to each other, we don't want this blue particle to be able to hop on top of the red. We want them to be sort of distinct objects. And so when they're next to each other, we set the rate to 0. That they jump to the side of the other one. So they can't jump on top of each other. So if we do this, with just two particles, you can get a nice mathematical equation. Where here the red term is the term from the movement of the red particle, the blue term from the blue. But notice we have these terms in here where we require that the site is not blocked by the blue particle for this jump to happen. And similarly here. So this stops it stops it being a product measure because there's some correlation between position. So with just two particles, this is fine. This completely describes our process. No real problem. But when we have many particles, when we have n particles, your mathematical equation, the dimensionality is going to grow with n. And so it becomes, as n sort of tends towards infinity, which often, for n is very, very large, which is often what we want to consider in these kind of systems. This becomes very computationally expensive, and also it doesn't particularly describe. We want to look at, say, the particle concentration, maybe the diffusion rate of an individual particle. These would be quantities of interest that aren't particularly described well by so can we do something to find the density of just PR? So this is the system we're going to consider. So we have two species, red and blue, where all the red particles jump with rate lambda r, all the blue particles jump with rate lambda b. And again, we impose volume exclusion. So when they're adjacent, they can't jump on top of each other. And what we're going to do, so the asymptotic quantity, that's kind of the assumption that we make, is that the volume fraction is going to be small. So we're going to consider our equation as an expansion in volume fraction. And so when the volume fraction is low, the dominating interaction is going to be between two particles. So we show this mathematically, but today I'm mainly going to focus on the method when you just have two particles and just state the results for when we have many particles. And so the quantities that show up in our equation for n equals 2 is two particle density, of course, but we're particularly going to be interested in one particle density. And so these are sort of probability densities. And so to find an equation for PR, we integrate out the second particle position from a master equation. So this is our master equation, but I've summed over xp. So on the left-hand side, we get the time derivative of the single particle density for a red particle. On the right-hand side, we have these sums that we need to evaluate. The blue term actually completely cancels out, so this ends up disappearing. And we're left with this red term. And when we sort of, these terms that we've missed out here, kind of add them and subtract them. And this ends up giving us this equation. And so this sort of grey box here, that's labeled the individual motion, is the same right-hand side that we had when we just had one particle. So this is sort of how a red particle would behave if it was on its own. But then we have an interaction term that comes from interacting with sort of the jumps missed because there's a blue particle in the way. And then we can do a similar calculation when we have an arbitrary number of particles. And it ends up looking like this, where sort of the interaction term retains the same structure, but now we have to account for there being more blue particles and more red particles. So there's n blue particles that can block a red particle. And then the red particle can get blocked by all the other red particles, but not itself. So because it can't get blocked by itself, that's why the minus constant. But this was sort of, we're going to be interested in taking h to 0, so this is okay, so we've now sort of got an equation for PR, but there's a problem in that it depends on the two particle density. And if we found an equation for the two particle density, it would depend on the three particle density, so on and so on. So this is kind of like the BB, KG, Y hierarchy, where normally what you do is that at some point you go, okay, well, I don't want to keep going. I may as well just solve the n particle problem if I was going to do that. So at some point, I'll make some approximation. So sort of cheapest one you might do is you might make a mean field approximation. So you'd assume that the two particle density is just the product. So you kind of, if you did this, you'd be missing out on correlations. So it does close your equation, but it's, you don't know that this is accurate. And in some systems it is. So if you have a very large number of particles, you take that limit, you can end up with sort of this propagation of chaos where correlations end up disappearing. This does actually hold. We're going to find out today that this doesn't work in our system. So if we did do this and we wanted to close our equation, this is sort of closed our interaction term, and then we plug in whatever lambda we wanted to, and we'd end up with here we end up with a cross-diffusion equation, where we've got the individual motion that we got before, but now with some interaction terms. We're here, phi r is the volume fraction, red, phi d is the volume fraction of blue particles.
These are no energies, they're just. Or can you write this as a gradient of that?
Yes.
But it just looks like an energy, but it's not.
Yeah, no, it's not. It's a very curly E, so it's not.
Okay, it's very good. Okay.
But yeah, this does actually. You can actually factorize this into a gradient flow.
Okay, that was my question, but it doesn't. Yeah, it looks like.
Okay, so this is what you get if you did the mean field approximation, but you have no control on the error, and we don't really know if it's accurate. So can we do something better? Well, here I say yes, we can. We can try using matched asymptotics. So the idea is that we want to find an equation for the two particle density, and we want to solve it. At least the leading order, and then we can have a sort of, because the interaction term appears at first order, we then have sort of first order approximation of our system. And so the the way we solve the equation for the two-particle density. So recall we have the math equation for two particles, and the leading order of 5. That's what we're going to get for any n really. But in this case, we'll focus on n equals 2 because it's exact. And so we split our domain into 2 regions. So this is kind of if we're in 2D space, this is the sort of solution space for the two-particle density is really 4-dimensional. So it's slightly hard to sort of show here. But we split this space into 2 regions. One where the 2 particles are sort of far apart, and then because here the interaction should be small. Then we rescale to some inner region where the particles are very close together. And here we change coordinates in the inner region. So we have x to locate the red particle, and then the rescale distance between the red and the blue. So hy. So when they're close, y is all to 1, x high is all to 1. And those are going to be like. Okay, so what happens in the outer region? So in the outer region, we pick an easy expansion in H, where note that these x's here, the 2 spatial coordinates of P out will be smooth, so they won't be discrete. And we guess this is our expansion. And then because we're in the outer region, we now use the sort of interaction part of our jump rates. And so this is actually just, we can just solve this with the product of, yeah.
Does it vanish identically, the interaction term, or do you make an argument that it's like of higher order in H?
So in the n equals 2 case, when the sort of the interaction bit of this equation is you require that the blue particle doesn't block a jump at the red particle, but because they're separated in the outer region, there's no chance that can't happen with the coordinates we picked.
Right.
So in the outer region, that term isn't there.
So it doesn't vanish.
So that's really going to come from the matching of the inner solution to the outer solution. Okay, and so without this here, at least at leading order, this can be solved by sort of the product of the single particle densities. And because we need this to integrate to 1, there's no like multiple in front of it. And so at least at leading order, this is going to be the product of our single particle densities. And this turns out this is all we need from the outer solution to evaluate the interaction term. But we'll need more from the inner region. So we solve this next. So in the inner region, we set up this inner solution. And I'm going to just look at the case where lambda is just a constant with the h squared, just to make it fit on the slides. Okay, and then if we transform the matrix equation with 2 particles, we transform it into variables. It looks like this. And then next step, we sub in an expansion for P in. Now note that first sort of spatial coordinate in the inner region is going to be continuous and like on the torus. But because we've rescaled y is now discrete and just in z to the d. And so this is sort of a feature that because we're on a lattice, this is true. And so at leading order, we actually get a very simple problem again. We just get a difference here, and because we need it to match the outer solution as we sort of leave the inner region, we get this matching condition. But note that this doesn't depend on y. And if we sub in something that's constant with respect to y into here, it's also going to be a solution. So we just get a very boring first order solution. But we need to go one order higher in the region. This is where problem gets slightly confused. So here we have the first order inner problem, and this looks kind of scary. So we have this kind of this operator really is acting on y. And so it might be easier if we simplify this first. So let's just look at the problem in y. So we've sort of extracted the problem in y. And here, this now lower the one is going to be it's a discrete class. And we can solve this. We can find this. It has sort of these properties where it's zero at the origin and has this plus or minus behavior around the origin. With b is given by this. That's not too important. And so what we can do is if we take the operator from the slide before, apply it to psi, we just get a multiple of this decay function. And so what does this psi look like? Well, what's interesting is this is really what's going to capture the it sort of has this kind of spike around the origin where this is really going to say that it's unlikely that the particles are going to be sort of so phi is kind of like pushing the particles apart in a way, more so than and phi is going to be the difference mean field. So if we plug this back into our problem, we kind of just end up with like a linear function in y plus this psi term. And this linear part is what you get from mean field. So if you sort of evaluated the mean field approximation sort of in the inner region, this is kind of what you get. And then this extra term psi is what's different from mean field. What's going to give us a different answer. So we can plug this in. So we can plug this into the interaction term, and the bit that we get is different is this alpha gamma, which is given here. And this is the difference between mean fields. The rest is the same apart from these alpha and gammas. So this alpha is positive. So this is going to reduce our sort of diffusion more so than we've got in mean field. So this is what we should have got the first time around. So we can do this generally for particles, but again, we're assuming we're in a low volume regime, and this converges to some volume fraction phi. That's going to be small. And so if we do this, we can do this with the general potential as well. We don't have to keep it constant. And then, yeah, degree terms are the terms that we would not have got with mean field. So these are the sort of bits that we missed with the mean field approximation. So this is sort of, I'd say this is the most intuitive form in terms of what order and phi things happen. But we can factorize this. We can factorize this into a gradient flow system where we have this free energy E and this mobility. And I think what's slightly interesting here is that the mean field approximation actually gets the energy right. So the free energy is the same in both mean field regime. I guess because the mean field sort of has the right steady state, so it should sort of get the right energy, I guess. But we see the difference here, the alpha gamma appearing in the mobility. And this is kind of like a envelope for mobility. And here's some sort of example simulation. So this is so I'm going to start with all the rail on the left hand side and the on the right hand side. Just let the system evolve and see how our equations do in the predicting complexity. So I've got some potential. So I've got potential pulling the red to the right hand side, and a potential pulling the blue to the left hand side. The solid line is our prediction, so the asymptotic solution, and the dashed line is what mean field we predicted. So sort of, as we might have guessed, in the low density, so this is phi 0.1 here, so 10% volume fraction. our asymptotics perform well because it's low density. The mean field is kind of not slowing down the particles enough, so that the mean field line is sort of ahead of where we might expect the actual solution to be. This is the average density across many simulations, and also averaged across the y directions. I say that so we have like vertical symmetry. So these are some results. But what else can we measure? So it's quite nice to measure particle density. We might also be interested in the diffusion of an individual particle. How does an individual particle behave? I'm going to measure the diffusivity. One way to measure it is it's like this. So we take the mean square displacement divided by time, and take this limit as t goes to infinity. So if this was a Brownian motion, this would be it's like Commun's diffusion constant. So how do we measure this using our set of equations? Well, we need to tag one particle. So we've only got two species at the moment. So we can tag one particle, and that can be our red particle, and the rest of the environment can be blue. And so we set we uniformly distribute the blue, so it's densities of 1, and we look at the behavior of one red particle. So we set the potential to 0. I'm just interested in diffusion. So the pink boxes are what contributes to its diffusion tensor. So this is it's diffusion on its own, and it gets slowed down by the blue particles here. So that contributes to this term. So this would be sort of first order approximation of self-diffusion. But we can do one better. So this is just a red and a blue environment. But maybe we want a red environment of red and blue. So how might we do this? Well, we could introduce sort of an imposter red particle. So we introduce a green particle that moves like a red, but we've assigned it a different species so we can keep track of it. So if we do this, we kind of extend our equation from 4 to now have any finite number of species. But here we just look at 2 species. So we're keeping track of a green particle and it's interacting with the red and the blue particles. And so here we can get a general diffusion constant. It's a first order density. So how does this compare to our simulations? We can run some simulations. And here we've got some different values of gamma that we might hit. So different ratios of the diffusivity of red and blue. We see that particularly at low densities it performs quite well. And it does start to peel off slightly at high densities, but we would expect this first order approximation. And again, the mean field approximation is sort of it's not doing well, but it's not a hard target to be, I guess. And yeah, and with that, I thank you for your time. Welcome any questions.
Let's talk. So,
For this mean field model that you showed, where you recovered the entropy and mobility. So just looking at the mobility matrix, so the terms that you see in the entropy, yes, I mean, these are the standard things to expect. For the mobility, so if you approach the maximum density, then you're getting in trouble.
Yeah.
Do you have any existence theory? I mean, if you drop the O to the power of 3 terms, so I mean, this is a gradient flow. Can you use unequals method bounded by entropy or anything? Is that okay? So have you looked at it?
I haven't looked at
Okay,
it, so I'm not
fine.
sure. Yeah, I don't know.
Because it has this gradient flow structure, and sometimes if you can bound the entropies, then there is some standard theory. However, your mobility doesn't look too nice.
Yeah.
So I was wondering if you have thought about existence of the PD.
Yeah, so I think, yeah, I do know that if you look at the asymptotic PD, when you look at high density, this it does go wrong because yeah, you can end up with this like being negative at like high density, I think. Which,
Oh, then you even have negative diffusion
we end up with
because the mu sigmas are where? Sorry, no, I got it wrong. Sigma the species. So then, but then this will give you then negative diffusion in the second term.
yeah,
And can it happen that it kind of heals the
Why negative diffusion on
Yeah.
the URs become negative? Then I'm not sure. I mean,
I'm not sure. I don't know. But,
then let's put it like these types of models usually they break down when you reach the maximum density, which would be rho equal to 1 or rho equal to 0. Just looking at the prefactor, it already looks like it could be difficult. But yeah, I was just wondering if you looked at any analytic results, or as I said, there's also you that has these methods where if you can bounce things, but if you have,
I think so. I think in the case where you have equal diffusivity, so d sigma dr is equal to dv.
Yep.
Then rho follows the heat equation.
Okay.
So the rho, your rho is smooth, and then you also know this turns this mu then becomes some form of the self-diffusion, which in the case of sets would prove it to be smooth as well. So you end up with a very, I think in the case where the idea of BV is very nice, but not in this case.
Did you perform any simulations? Like when you approach these maximum density cases?
No, so we mainly looked at low density.
Only low density.
It becomes.
I know that it doesn't describe the system very well anymore. I mean,
so
just curiosity.
We did do some stuff where we, in the case of the R equals to DV, we've done more stuff because we could get a more global approximation. But yeah, I don't know in the case of
I think at the beginning you mentioned that there's some, you're trying to maintain low density. Did you say what the asymptotic relationship between what the asymptotic density should be as h goes to 0?
So do you mean here where we say this should converge to simplify?
Yeah, I think so.
Yeah, so this
is probably just some scalar.
Yeah, so some scalar, but some scalar that's small. So it also
okay.
Yeah. So then the expansion comes in phi, yeah. So
okay. So it's
phi
not necessarily sensitive that like n should go as h to the 1 minus e or something like that.
Yeah, no. So yeah, as long as you can take some wacky limit, I think, as long as this quantity to always be like asymptotically small.
So the approach is to a finite value where h goes to 0.
Yeah. So so we want to sort of as h goes to 0 and sort of well, you can either have this phi could be 0 as well. You could just let this go to 0. But you can n can also go to infinity. But in such a way that this sort of remains finite.
You don't see like qualitatively different. I'm sorry if you already answered these two questions, but you don't see like qualitatively different behavior when the asymptotic density is 0 versus some finite value.
Well, it would be different, right?
Okay.
So it would be as though if it goes to 0, it would be as though that species isn't there with respect to the. Like you just get a different equation, right?
Okay.
Sort of as phi gets smaller, there's less interaction. So it's these interaction terms. If phi gets small here,
yeah.
So if phi was very small, maybe the blue interaction term would have more of an impact.
Oh, okay, I see. Yeah.
Other questions? If not, thanks, James, again.
Yes.